Good morning. So before I start, as usual, I will have to summarize first what we talked about in the last class. Um, so a few things about what we talked about in the last class. In the last class, we finished the entire code without using any libraries for forward propagation and backward propagation. Okay, we looked at both the codes for backward and forward propagation. And we talked about all the way the delta works back. So what we are going to do is we are going to start with the code and explain how it all goes back. But before that, I'll give you an insight of the data structures which we are using. They're critical to understand what data structures we have used so that you take it forward. So today we are going to take a step forward and talk about the various kinds of gradient descents. We are going to talk about the stochastic gradient descent. We are going to talk about the mini batch gradient descent. Then we are going to talk about the momentum gradient descent, and then we are going to talk about the learning decay incorporation in the gradient descent. So those are all the next steps of AI. And I am hoping that once you follow these lectures properly, you will be in a great shape to do good amount of AI programming. But since we are on that topic, I think I would want to start this by saying a few things about the way we plan to do AI in the next semester. I think I'll take a few minutes to illustrate before I go here. See, we have now about 8 potential startups which are getting incubated. I'll just mention that and then I'll go back to what I'm doing, because all of these are AI oriented. We have 8 startups getting incubated, and all of these need heavy duty AI. So the first startup which is getting incubated, I am sure all of you are aware, which uses a huge amount of AI, is the drug discovery startup, which we call, all of them are called paradigms of one sort or other. So they are called drug paradigm. So this is already getting company getting incubated. Soon we are starting, no, we have already started letushack.com. Again, this uses AI, but this is basically a cybersecurity platform, cyber security platform. Then we have roboparadigm.com, which is towards robotics automation. So it's called robotics automation, where last week I saw a lot of good work happening there. And during these course of this lecture, I will also, not today's lecture alone, but in general, today I'm just giving you an introduction, but over the weeks, I will also tell you about the progress we are making in each one of them, what we are actually doing. That might be interesting for some of you to understand and see how we are going forward. So Robo Paradigm, these are already in play. These all 3 are in play. And the ones which are coming up in the next semester are the following. There are going to be interesting ones coming up soon. One is called, we haven't given it a name, but it's a thing in material science. We're creating a new startup in material science that is basically creating substitutes for rare earths, substitute for different kind of batteries. So, and I'll tell you about the progress we make in each one of them every week through this talk. Also, in addition to giving you AI background. So because you also must know how this world is evolving, because this is a quickly evolving world. So that's material science. It will look at different kinds of use of AI for creating new materials. And this is yet to start. This will start in the next semester. Then there is a thing which is also going to start in the next semester. It's called NOAA paradigm. not new paradigm. It's called Noah paradigm. This is about fem health, feminine health. That is everything to do with PCOS, anything to do with PCOD, PCOS, basically fertility, hormones, that kind of story. Nua means basically feminine paradigm. In Vietnamese, that is what it means. It addresses feminine health. That is Nua paradigm. And then there is neuro paradigm, which is addressing mental health, autism. These startups are coming up. And then there is something called agro paradigm, which is to aim at agriculture applications of AI. Okay, so these are the startups. This has also kind of started, but we are still struggling with it. But these going to start with the next semester. Agro paradigm has also started. There are some interesting projects they are doing, and these are yet to start. This is start, and most of them are slated to start, or rather, all three of them are slated to start in January. So that's the way we are going about. I think I'm missing one. Not sure which one. Huh? Telepad. न्यूरो आ गया, एग्रो आ गया.
I think dyslexia का कुछ है सर.
हाँ नहीं वो न्यूरो पैराडाइम. न्यूरो पैराडाइम is the mental female health. Material science is there. Oh yeah. I found more. We have launched another project. This is not a. This is also making of an LLM for corporate thing. This is very interesting. The project is called GOGTE. This is launched with an American company. It's an American collaboration. Okay. So this is called GOGTE, and this is basically we are taking DeepSeek here and developing it. So this is also being launched in the next semester. So this one and these three are going to be launched in the next semester. These remaining are already in action, and they're doing some work, some interesting work. They'll do some more work as they shape up. So these are all, by the way, all are AI and deep learning. You know AI, you can do stuff in any of obviously you can't. So that's the moral of the story, and that's what we are going to do. Okay. So this is just a thing, and I will drop a few lines on the progress of each one of them as every week as things pass. Fine tuning of weights of trained LLMs for niche cases. Yes, that is what GOGTE does. It will take DeepSeek's basic algorithm. Basically, I don't know how well you guys know LLMs, but I'll cover the LLMs. But it's you know, what is the DeepSeek's key value? DeepSeek's key value is primarily what we call the mixture of experts, and we want to grow on that mixture of experts story. Actually, only at this stage, only DeepSeek has it. The rest of the guys don't seem to have it developed. That works very well for us for the GOGTE story. Will second year students be able to join? This is meant for second years to join next semester. Yes, we are looking for expanding the program. We will come to you for adding people to these new projects. For GOGTE, we are looking for people. We are looking for people for material science, Noah paradigm, neuro paradigm. Only thing is for Noah paradigm, we are expecting only girls. So this is a girls only team. Girls only team. So that is about feminine health. So I think we will put that restriction. But the rest of it are open, and this is also open for girls. The rest of the open are open for everyone. So these are the plan for the next semester. When is the second semester? I know you know it better than I do. I don't know.
No, sir.
Will 2-2.
2-2.
Acha, when you say second semester, oh, I meant second year, second semester, not second semester, not first year, second semester. No, this is second year, second semester. No, we don't currently have any plans to incorporate first year students. Okay, so that's pretty clear. First year students must specialize in their next semester. See, actually, you know, I have a very simple thing. By the end of first year, you should know maths well and programming well. Okay, if you, since you are on that topic, let me say the way we think. At the end of first year, you should know Python well. First year, you should know Python well. From the end of second year, you should know AI very well. You should be master of AI by the end of second year. By the end of first year, you should know Python and certain amount of digital data structures.
2-2 starts from 19th January.
And I think for different people, 2-2 starts at different times. Okay.
For the KMET, it's
So depending on when it starts, we'll do it. Okay. Yeah. End of first year, you should ensure you're good in Python and data structure. And here, one thing I'll make it very clear, this should happen irrespective of which college you are, under which teacher you are. See, this binding to my teacher taught me or my teacher didn't teach me is bullshit. I'm not, we're really not interested. The time is past for that. If you're a victim of your teacher, so be it, enjoy it. And we can't help you. This is what the moral of the story is. That is why I'm very particular that in this semester, in this year, at least you should be a master of AI. Okay, you should know AI like the back of your feet. Okay. We will decide what the selection process is depending on the common denominator. See, if it doesn't have to be JavaScript, it has to be Python. Okay, so you should know Python very well. The problem is people don't know one programming language well, and they want to do various things in AI and all that kind of stuff. I feel very miserable, you know, doing that. So either you know Python or you know JavaScript. One of them you should know well. And if you don't know both, then you jump in a lane. I mean, what can we do, correct? So, and this is irrespective of whether you are got a teacher to teach you or not. I don't like people when they say my teacher did not teach. You know, you should not be dependent. Okay. Yeah. Yeah, for project school, we'll take overview from next semester on Monday and Friday. Yeah, I'll take that. Oh, this is just an overview. I'm not going to teach. Okay. Okay. So this is a plan for the next semester. I think this was also to wait for students to join this session also. So no, I'll keep giving you updates on the 8 paradigms that we are starting, 8 startups that we are starting. Every week, if I can, at least give you a little bit of things so that you are able to understand what's happening in this business and in this industry, because the earth is moving very fast in this area. Okay. So, yeah, this is from next semester, correct? Okay. Now we will continue with our AI story. Now I'm going to briefly talk about what we have already finished in AI. We will see the original code. I'm going to walk you through the original code, and then I'm going to tell you what changes I'm going to make and why I'm going to make those changes. So we have not yet go to TensorFlow. I am going to do it later, next week perhaps, because once you understand why TensorFlow is required, then only TensorFlow makes sense. See, people use TensorFlow nowadays as if they started life with TensorFlow. No, that is not how it should be. So we walk through the program. Achha, those of you who can't see this screen very clearly, my suggestion to them is that please open your browser in some other window and look at this code, because I'm going to walk through this code very quickly in about 5 minutes or 10 minutes. Just tell you what are the nuances of this code, which we already talked about, but I keep talking about it. So we will go ahead and do it. So you know, we are building a neural network for analysis, and we are for which has one, you know, the structure of our neural network. We have an input layer, we have a hidden layer, and we have an output layer. And everywhere we have used the activation function as sigmoid of x, which is 1 by 1 plus e to power of minus x. Okay, and now let's go about creating the network, and then we will talk about the changes which we are doing. So very quickly, next 10 minutes, I'm going to talk about the existing network. Then I'm going to talk about the changes, talk about the concept behind the changes, and then how the changes are going to be made, and then we will proceed. Okay, so here is the network. So the network is a collection of layers, is a list of layers. You can see there, and currently, how many layers are there? Only 2 layers. We don't count the input as a layer, this layer and this layer. This is called the hidden layer, this is called the output layer. So currently, this is the hidden layer. So hidden layer is also a collection of neurons. Network is a collection of layers. Each layer is a collection of neurons. Each neuron has, each neuron here has a representation as a dictionary. One of the elements of the dictionary, one of the key of the dictionary is in, if you visualize from a JSON perspective, one of the weights in the dictionary is weights. One of the key in the dictionary is weights, and against the weights, I have a list of weights associated with the neurons. That is what we have. Now, if you were to think with these terms, if these are the inputs, and this is one of the neurons, this is one of the neurons, if you visualize it from that perspective, with each neuron, weights are associated in this manner. These are the weights associated with this neuron. Similarly, there will be weights associated with this neuron. So when I represent these weights over here, I am referring to the weights of this, and this is the hidden layer, and these are the weights associated with that. And this goes on. This is this layer. Then again, I have the other layer. Again, it has a dictionary. It's a list of, sorry, it's, with each neuron, there is a dictionary. So because I hope you are clear, this is, these are the network. This is the layer. And inside the layer, oh, I forgot to show this, but there is one more level where I have, because each layer is a collection of neurons. Each neuron has, is represented as a dictionary. So each neuron is represented as a dictionary. Okay. This I have been explaining earlier also. Currently, the dictionary has only 1 weights. Actually, it has little more. And then it has basically the list of weights associated. Okay, and this dictionary grows as we expand. Okay, so this is the primary data structure. Okay, now this data structure kind of expands as we go through the code, and you will learn more about it. Now we have code for activation. Remember the way the activation happens. There are 2 things which we do. There is linear and non-linear. Right? Remember, and there's linear activation and non-linear activation. The linear activation is represented as Z1 or Z of whatever, Z of I or whatever, sigma Wi Xi, if you take the sigma of I, and the plus bias. Okay, that is Z1. And the non-linear transformation is basically sigmoid of Z1. Is what is the non-linear. So the non-linear is captured through the sigmoid, and Z1 is captured through this linearity. So this is how it is. So this basically captures both the parts. So if you see this, this is capturing the non-linear, sorry, the linearity, where I have weights and I have inputs. Every layer has its weights and its inputs. For this layer, these are the weights and these are the inputs. So the outputs of the hidden layer are the inputs of the output layer. So it just goes on continued. And if this can be 1,000 layers, then this is 1,000 layers. Okay. So this is what we had discussed in the last session also, in the last session before that also. So activate is doing all of this. It's multiplying this Zi, Wi xi plus B1. So it's doing this part. See the way it is doing. Weights it is taking and inputs it's taking. So weights and inputs, and then it is taking the last weight, which is basically the bias. So it's starting with the bias and doing for I in range length of weights -1 activation plus equal to weights of I into inputs of I. So this is Wi xi. This is how the multiplication is happening, and it's returning the activation. And then you have the Z1, which is application of the sigmoid. This is the Z1. So this is giving you the Z1, and this is giving you the activation. Well, some people call this the linear activation, and some people call this the non-linear activation. I think that is a better way of calling it. So you have the sigmoid of Z1, which takes this and computes the sigmoid. So that's how this whole story happens. So this is 1 by 1. The sigmoid definition is 1 by 1 plus e to the power of minus x. So this is what it is. Of course, here x is nothing but Z1, which is there, and it does. Then we talked about the forward propagation of the network. Okay. I think we will clear this and talk about the forward propagation. So this is the forward propagation. This is a forward propagation network. So just understand how it works. So it takes two parameters, the network, which we just created, and the row, which is the input. It takes one input at one row at one time. Just now try and understand the flow. Input is equal to row for the first time, then goes through each layer of the network. Remember the layers, the input layer, the hidden layer, and the output layer. Here there are only two layers because the input is not counted as a layer. For each neuron, it goes layer by layer, and goes then neuron by neuron in that particular layer. So for each neuron, what does it do? It first computes the Z1 by taking all the inputs, multiplying with the weights associated with that neuron, because this neuron has weights associated with each of the inputs. So it takes that, multiplies it with the weight, takes the input, multiplies it with the weight, it will get the Z1. This is to get the Z1. So activation is equal to activate neuron weights, take the weights of this neuron and multiply it with its inputs. The original inputs are the row, which is the taken from the incoming data, the sample. And after that, for every layer, it computes, for every neuron, it computes one output also. So now the neuron has, the neuron dictionary has two outputs, each neuron. So far, it had only weights, remember? It had weights in its dictionary for every neuron. Now it also creates another entry into this dictionary, which is output. So every neuron, now it produces an output. What is that output? For example, here is the output of the hidden layer. Output is produced by taking the activation. This is the Z, and taking it and multiplying it with the transfer function, which is the sigmoid. So this is the sigmoid, and that is how you get the neuron output. So that will be the output of this neuron. Like that, you compute the output of every neuron in every layer based on the input, and then make that as the input. So this output, which is output right now, which is what we call new inputs here. Now you make that as the input for the next layer, right? So you build the new inputs as an output for this layer and make that the input for the next layer. That is what is happening here. Okay, so this is the forward propagation. And it goes through all the layers, and that is the final output. This we did 2 weeks ago. Okay, now we have to work towards the backward propagation. Backward propagation depends on computing of the transfer derivative. Now here things start getting a little hairy. So I will now try a little insight from you, and then let's see what we do to compute the output. Let me first talk about the theory of the output, and then I'll talk about the logic, because it's imperative that you understand the logic. Okay, now I'm going to pause here and ask. Okay, now this is the backward propagation. Okay, now in the backward propagation, I am adding. Okay, now so far each of my neuron has in its dictionary how many keys? Well, wait. It has weights as one of the key. Yeah, I want you to understand this data structure well. Weights is one of the key. The second key is that of output. That is the output of the neuron. So the output, each neuron has only one output. It has many weights, but it has only one output. So this is a scalar. Output is a scalar. Okay. Now, if you look at this code, can anyone tell me? Let's see how you are. Okay. Let's anyone tell me? Can anyone tell me after this has been done? How does each of the neuron look like? We'll have to keep the chat open. After we are done with this backward propagation, how does each neuron's dictionary look like? Is it going to look like this only? Or is there going to be a little change to that dictionary? It's imperative that you understand this. Each neuron, there are neurons in the hidden layer and there are neurons in the output layer. So how is the neuron of each layer? What is the change we are doing looking at this code to the neuron data structure, to the neuron dictionary after this code, after the backward propagation is done? Anyone? You can write there. Okay, good. Weights, output, delta. Very good. Good. Good, guys. Some of you are getting the hang, and I am sure. I will tell you one thing. If you understand this flow and this flow only, you guys are going to understand AI at its full level. If you miss this, believe me, you will never understand how ANN works. If you don't understand how, as I keep saying, if ANNs work, you'll never understand how the complexity of algorithms which we need for our various startups is going to work. You'll never get it. Okay. So it's imperative that we understand. Okay. Yes. So we have added another field into our each neuron at the end of the backward propagation, and that field is delta. Okay. Now let's observe carefully. How is that delta computed? It's computed in 2 steps. I went through this code in the last class. I was hoping that a lot more people would have got this, but anyway, this is what we have at the moment. We cannot ask for or improve the level of the students. I'm trying, as you can see, but we will see. Okay, so backward propagate error. So these are the expected values at the output layer. Okay, for each of the neuron in the output, what is the expected value? This can also be a vector or a list depending on how many outputs are there. Typically, we treat it as a list. So now we start working backward from the end to the coming down. Yeah, somebody asked a question. Does the forward propagation weights forward propagation disappear when backward propagation delta comes in? No, they don't disappear at all. They stay there as another key. Okay, weights are very important. Weights will continue. They get updated actually. The old weights, if you're asking, yes, they get overwritten, but that's precisely what we are trying to do. Okay, but please understand these data structures very, very intimately. Because if I have ever to make a good AI engineer out of you, if I have to make a good AI engineer out of you, I will need you to understand these data structures very well. Otherwise, you know, in AI, there are a lot of people who just use AI at a very superficial level. They are not going to become rich. You know, who is going to become rich in AI? The uh, Sam Altmans of the world are going to become rich. And they are the guys who work at the kernel, at the core level of AI. And this is how they think about things. Okay. Anyway, so let's go work backward. Network, expected result, expected output. Now see the way it goes back. For I in reverse range length network. So I'm going in the reverse network. So layer is equal to network I will be the output layer currently. Okay, it will be the output layer because I'm looking from the layer backward. Now I'll compute the error, which also I'll start as a list for I equal to length network minus 1. So I will not start with that. This is when I is not equal to length of network minus 1. So we are not at the output layer. We are at the hidden layer or the input layer or the input. Then this will work. But we are now right now at the output layer. So let's look at the else part of the code. So right now we are at I equal to the length of the network, because remember we are going in the reverse range of data of the reverse of the range of length network. So if the network has a certain length of 5, we are going from there backward in case it is. So else, we are in the else part. We are not fulfilling this part yet. So what are we doing here? For J in range length of layer, that means J is going through every neuron. J is looking at every neuron of the output layer. Every neuron of output layer. Yeah. So I look at first the layer of the output neuron. Neuron is equal to layer J. Yes, I'm at that neuron. Then what do I do? At every neuron, I accumulate the error. So errors dot append. So whatever is the error which is done in that output layer, append neuron output, which has been computed during the forward path. There is some value here, scalar value. Neuron output minus what was the expected output. I accumulate that as error. Okay, I have accumulated that as error, which has been caused at this neuron. Okay, for every neuron, what is the error? E1, E2, like that. So these are the two neurons in the output layer, and this is the error accumulated at each of the neuron. Okay, or the error encountered at each of the neuron. Okay, so this is how the error is computed for the output layer. Okay, now this is step 1. But remember, error is just accumulated in a list. I'm not storing it in the neuron. Then I'm only accumulating the error in the neuron this way. Okay, and for the rest of the layers, that means not the output layer. The error is accumulated in a different way. And I think I gave you the logic for that, but I don't mind giving you the logic again. So this is for the output layer. The layer is error is pretty trivial to accommodate, or trivial to I would say compute. This is the error, the way it has been computed. Now, if you look at the non-output layers, okay, now the hidden layers, okay, this one. Now I look at this. See the way error is computed. Then we'll come to the last part. Error. See the way the error is computed. Again, it is going through every neuron of the inner layers. Okay, because there may be many in real life. This will always be one. There will always be one output layer, but this can be many. Especially if it is a deep network, this can be really many. So if that is the case, again, I'm going through each neuron of one of the inner layers or the hidden layers. And now I'm seeing for each neuron in network I+1. So for computing in each of the inner layer, I'm looking at its neighbor. I'm looking at its next neighbor. For each neuron in network I+1, I'm now taking that neuron delta. Before that, I think for the outer layer, we would have computed the delta, and that delta is used to move the error back. But I'll come back to it in a moment. Let's go, because see, first after the final layer has been computed, its output is computed, this code will anyway get executed, right? Because of the loop which is here. This is inside the loop. So this code will get executed for every layer, including the output layer. So see what he's doing. We will understand this code and then go back to this code. So see this, for j in range length of layer. Right now we had processed only the output layer. So the layer we are on is the output layer. When we looked at it first time, neuron is equal to layer j, and neuron delta is equal to error into for every neuron we have accumulated the error. This is the error on the first neuron, first output neuron, and this is the error on the second output neuron, if there are two. And what are we doing here? Neuron delta, we are adding to this error, to this now, neuron delta is equal to error which was encountered there, but we are not taking the error as it is. We are taking the error as it is and multiplying it with the transfer derivative of neuron output. So whatever was the output at this layer, we are doing that. I think you know the logic behind it. Some of you will remember the logic behind it, because the logic was, when we compute the weights which have to be changed, the dou L by dou W. Now look at it at the outer layer was dou L by dou O1. I mean, if you take the first neuron, dou O1 by dou Z1, because that's how we do it. And then, pardon this drawing here, dou Z1 by dou W1. Okay, so that is how dou L by dou W1 will be. Now, dou L by dou W1, you remember what we had done? If you, those of you remember, will remember this as a derivative with respect to O1 of the output mean square error. So that was O1 minus E1. Remember, this was the error. That is the output minus expected. This was the expected value. This was the actual output. And those of you who are keen computer science guys and maths guys, dou L by dou Z1 was O1 into 1 minus O1. This we had computed last time. And then dou Z1 by dou W1 was its input, whatever. So the hidden layers output, H1. So this was the output, hidden layers output, H1's output, which was connected to this. Okay, so this is what was used as our equation. Now, if you see, what they are trying to do is, this was before I update the weights. So what they are doing now, look at it very carefully. Now, what is this errors J? This is O1 minus E1, correct? The errors J is O1 minus E1. That is how the error was computed. Neuron output minus expected. This is O1 minus E1. Think of it like that. O1 minus E1. This is how this has been computed. Then times transfer derivative. Transfer derivative means the, you remember the transfer derivative of the sigmoid. So this is O1. So transfer derivative of the sigmoid, remember, was what? The derivative of sigmoid is sigmoid into 1 minus sigmoid. So that was O1 into 1 minus O1. So this term has been captured. Now, if that is multiplied with that layer's input, we get our dou L by dou W, which is adequate enough. So we have split this into two parts. So this, they call it as delta. So this is what we store for every neuron in the backward propagation. Because with this, if you multiply this with H1, that is its input, you basically get the update you have to do. Of course, you still have to do that new and dou L by dou W and all of that, and then update that weight, right? So we will come back to that. So O1 minus E1, O1, 1 minus O1. That is how this is come. So this is the delta that we get computed. So with the, I just changed the color of my pen a bit so that it stands out. And this is what is being brought as the delta. So this is delta. I know this is for those of you who are a little bit dense. I know this will be a little tough, but you know, you have to become rich. You need to have a very strong maths in AI. Today, if you go to any IIT and you say, I want to learn AI, they'll say, the professor there will ask you, are you good at maths? If you're not good at maths, don't come into AI. Learn to use ChatGPT and that sort of thing. That will be fine. You know, use AI at a very superficial level. Feel happy about it. Generate a few pictures, generate a few animations, and enjoy. Okay, so if you really are smart, then you really have to follow this maths. There's a lot of maths, and it's all fun. So this is O1 minus E1 and O1 into 1 minus O1. So that is what is captured as delta. If you multiply delta with H1, you'll get the dou L by dou W. That is why we are capturing. So this can be multiplied anytime. So for every neuron, if you see, the effort is on to accumulate its delta, to build its delta, which can be easily built from errors J. For every neuron, it can be built by multiplying the error, that is O1 by E1, into the transfer derivative of the output. So this we already have. So we have, from this we are growing this by applying error J. Error J is this O1 minus E1 term. This is for the output layer. Okay. Now, how does this look for the hidden layers? Okay. So I know I have crowded this screen further, but I'm going to crowd it a little more. We're going to finish understand this. I'll tell you, if you understand this part, your entire, I would say this is 40% of your AI. You get this, that means you have mastered backward propagation. I always ask, how well do you understand backward propagation? Only when you understand backward propagation are you an AI engineer. Okay. Everybody else is a joke. Okay. This I'm just giving you motivation so that you can get there. And that is also quickly enabling a lot of people to desert me because they have decided this is not. I thought computer science is a piece of cake. I thought if you just pay fee and sit in class and see things, it's over. Okay. Well, they are disillusioned. If I not equal to length of network minus 1, this is what it is, then I'm looking at the hidden layers, in inner layers. So again, I go through each neuron. So when you say for J in range of length of inner layer, you're looking at inner layer neuron. See the computation there. We make error there 0. So now comes the intuition. This part is the intuition, very, very important intuition. This intuition is what? See, this is the delta for each neuron in its output. So in order to compute the error for the output layer, it was looking at the expected output. Whereas for the hidden layers, there is no expected output, right? There is only the output from the next layer, which it has to look at, and from there it has to work backwards, and the delta for the output layer. So the argument is like this. I'll try and draw here, and this argument I had explained to you last class, but since it's important, super important, I'm going to explain again. So for the output layer, I already have with each of these neurons, I have deltas. Okay, I have computed. That computation for the output layer I have done. Now, each of these neurons here have contributed to this delta. Each of these delta has been affected by this. Okay, so this deltas which happened here in the output layer, each of these neurons is a cause. So there is a weight here, and let's say there is a weight here. Okay, now the way this delta is carried back in the backward propagation is proportional to the weight which is connecting this delta to this neuron. See, this weight is connecting this neuron to this delta. So the amount of this delta caused by this guy and the amount of this delta caused by this same chap is actually, so if this is delta 1 and this is delta 2 caused at these neurons, then W1 delta 1, W2 delta 2 is the delta for this chap, because he caused these deltas to happen, these errors to happen. Deltas are not purely errors. There are errors married with the derivative, this transfer derivative or derivative of the output. So this is delta 2. This is the delta accumulated here. Think of it as error or some kind of computation of the error. Now the error which was caused here, this guy was a causative, this guy was a causative, this guy. Now we have to somehow transfer this delta back in the backward propagation. It's called attribution. So the way I will transfer it is, I'll multiply the weight which is connecting this, take that, pull that backward, take this delta and pull it backward. So these two guys, so these two deltas will, depending on W1 and W2, will pull that deltas back, and this will be the delta for this neuron. So this is exactly what is happening. See, it's looking at the neurons for each of the neuron in each layer for this neuron. It is looking at all the neurons in the subsequent layer. See this. For neuron in network I+1, I am on a particular layer. For each of the neuron in the output layer, I am now computing the delta. First, I am computing the error. The delta computation is at the end. So I am computing the error. Error is what? Error is this delta into W1, W2. Okay, look at this. Neuron weights J. That is, weights J is what? Weights associated with this jth neuron. This is the jth neuron of this layer. Okay, so I am looking at the jth neuron of this layer, and I am looking at the next layer's deltas and transferring that delta back. So this is how the error is accumulated. So this error will be sigma of Wi delta I, Wi delta I, W2 delta 2, like that. Okay, if you look at it that way. So this is how the error is accumulated. I am appending the error. So for each of the neuron, now I am accumulating the error. So for each of the neuron, I am accumulating the layer. And then once I have done it for all the neurons in this layer, again I compute the delta. Delta, I use the same equation. I use error into, so here the error will not be this for the hidden layer. For the inner layers, this is only for the outer layer. This will change. This will be this error. The error which has been passed back thanks to the deltas, that error will come back, and that the error into this neuron's output. Here, now this neuron's output, which is the hidden layer, into 1 minus O1, that we retain. Okay, that is the output equation. So that is how this neuron delta for these people is computed. So now, so it is different for the inner layers and outer layers. Inner layer is this, outer layer is this. Outer layer is very simple. Inner layer, to understand, you have to take the same thing. In place of errors for the inner layers, we are taking the deltas which are pushed back, pulled back, that we are taking, and that we are retaining the neuron output. That is same logic which we use for the outer layer also, for the outer layer. That neuron output, we are taking it. Whatever is the output of that layer, we are taking it and multiplying it. Okay, so that is how deltas have been computed for each of the layers. Okay. Okay. Now I will look at one piece and then I will pause a bit. So now that you have got the deltas for each piece, what you have to do? You have to multiply the deltas with their inner weights. If you multiply the deltas with dou Z1 by dou W1, which is their inputs. Dou Z1 by dou W1 is always input, remember, because Z1 is what? Wi xi. Whatever is the input of that layer, we have to take and multiply. So if you are going to multiply that, then it's pretty easy to now compute the updates to the weight. Delta is a shortcut to, if you multiply delta with the input of that layer, you get the update that has to be done. That's why most of the algorithms in AI you will see will focus on computing this delta. Okay, so now I think we will look at update weights yeah. So look at the update weights which happens, and then we'll talk about training again, and then we'll talk about the change which we want to enact. Okay, now let's look at update weights. Okay, what is update weight supposed to do? Change the weights. What is the abiding equation for changing the weights? The abiding equation for changing the weights is weight new is equal to weight old minus new times these people, some people call it neta, new. It is going with various names, so whatever suits you. Some people call it n also. Okay, I think it is called most popularly as eta, eta. Some people call it something else. Depends on all this. Also depends on when did you first attend maths. I'm an old maths guy, so I call it new, but you can call it something else if you want. New times dou L by dou W, which is dou old, this weight of old, because you don't know new yet, which is also can be written as W old minus new times delta of that neuron times its input, the input which has come to this layer. That is what will get you dou L by dou W. Delta times delta of that neuron and associated with that weight times its input to that neuron will give you the change which has been done to the weight. Okay, so that is how the weights will get updated. Now I hope you understand when I say input to that neuron, because every neuron will have its own input, all the inputs actually. So it will be all of that and multiplied. So let's now look at how it has been computed. So this is basically what they'll try and do. Okay, inputs for the last layer, the input is row minus 1, which is the input is for the first layer. The input is inputs is equal to, this is to remove the output. The last column is the output, so that's why they remove the output, and now they are ready to update the weights. So they take the input because input is needed. Now they say for I not equal to 0, for I not equal to 0, yeah, you don't do anything for the first layer, because input layer you don't do. Inputs is equal to neuron output for neuron in network I minus 1, because you have to start processing from the first layer, not the input layer. So input layer is called the first layer. So inputs is equal to neuron output if it is the second layer. For the first layer, inputs is already set. Inputs is equal to neuron output for neuron in the network and I minus 1. This should make sense. For the first layer, the input is the actual input. For the subsequent layers, the input is the output of the previous layer. See, for neuron output for neuron in network I minus 1. That is the input for the subsequent layers. Now, what do you do? Now that you have established your input, whatever it may be, depending on whether you're layer 1 or, the first hidden layer or remaining. Now, what do you do? For each neuron in network I, now we proceed for J in range length of inputs. Now you're doing the beginning to do the computation for each of the input. Neuron weights J, because those many inputs will be there for that particular layer. So for J in range length of inputs, now you understand what's happening here. So you have the hidden layer first, you have the input layer, and you have the output layer in this kind of a network. So first you have to update the weights connected with this neuron. You have got a delta associated with it and all of that. Now you have to update this weight, okay, this gate. Now what is this weight? This is the weight connected to the first neuron of particular layer. This weight you have to update, then this weight, then this weight. So for J in range of length of inputs, so you're going through all the inputs so that you go through all the weights associated with the first neuron, and again you have to do this loop again and again. Now for this layer, you are now going through all the inputs. You have to update all of these guys. For j in range length of inputs, now you say neuron weights j, the new weights is equal to whatever the old weights, neuron weights j, whatever the weights which were there here associated with this neuron. Uh, uh, you start processing it minus times learning rate, that is the new, this is the new, times neuron delta into inputs j. So you have got the neuron delta for that and input j, that will cause this weight to update. The update which will be applied to this weight will be dependent on that. And for this is for the bias. Okay, keep the bias out, that does not have basically any input, so it's a fixed just neuron delta for that and multiply. So let's ignore the bias for a moment. Let's not cloud it. So I think we went through this last time, that weights j, length neuron, and all that. Okay, so this is what we had described to you. So I've just kind of re-explained what I did in the last class for the last 1 hour. No, for a little less than that. Now I'm going to ask you whether did you understand the computations of delta somewhat, and how that delta computation is being used in update of weights. You have to understand these two things. How was delta computed and how was updating of weights applied. See, the updating of weights depends on the input also, because that's how the equations are. The equations dictate that the input is taken into consideration while computing the update to the weights, because of the dou L by dou W equation, which also takes into consideration the input if you derive it. Okay, let's see how far you have come. No, it's easy. It's done during backward propagation only. It's part of the backward propagation. It's done in 2 steps. When I show you the code, you will see that it is done in order to simplify the logic. That's all. Okay. We are ending the poll. Looks like majority have understood, whoever is. Okay. No, enough, guys. Okay. Now, I'm going to ask you a question and pause a bit. Think and answer the question. Just don't answer the question because you have to answer the question fast enough. Take your time and answer this question. The question goes something like this. Yeah.
They can type their answer.
They can type their answer?
Yeah, we can post a question, they can answer
Okay.
it.
Okay, I'm going to ask this question. So listen to the question very carefully. Now, I want you to look at the part of the code which is currently on the screen, but you may have it also, which is called training the network. Okay, training the network. Okay, there is something you will see there called epoch and all of that. Okay, now I am going to so what this is doing is it's writing the path for training the network, and train is actually the array or the list of data. So train is the data, and which is basically the data set. If you want, the data structure for that data set is shown at the bottom where you see data set. That is what train looks like. Train is training data, basically training data set. That is what is train. Okay, so there is network, there is train, there is learning rate, there is number of epochs. That's number of times we use this training data set. And then there is obviously outputs, which is what the train network does. If you look at the code which is on the screen currently. Now let me come to the question. The question is, let's say the training data set, listen to me very carefully. For example, in this case, let's take this example. The training data set contains how many rows? 1, 2, 3, 4, 5, 6, 7, 8, 10. 10, huh?
10.
Okay, let's assume that the training data set contains 10 rows. And let's say the number of epochs is 5. Okay, listen very carefully and answer. The training data set contains 10 rows. Okay, and the number of epochs is 5. Number of epochs is, let's pretend it is 5. Okay, for lack of any better value, we'll give you the number of epochs passed to this thing is 5. Now you have to tell me how many times are the update to the weights, how many times are the weights updated in this current scenario, in the current way of doing things. Look at the code in front of you, train network, and answer this question. How many times are the weight updated overall?
You have given me a question in Q&A. Please look at the Q&A. Try to answer that.
Yeah, you can answer there or here, doesn't matter actually. Okay. I think we got our answer. The number of times the weights got updated is 10. Okay. Sorry, 50. You're right, 50. How is the 50 coming? Because we are saying that the data set contains 10 and epochs are 5. So for every epoch, for every row, so the moral of the story here is, yeah, most of you got it right. Almost all of you got it right, whoever answered. Okay, so now let's analyze what happened. What happened? Okay. Yeah, sorry. Seems like we lost the current here. I don't know whether the same thing happened at your end, but we lost current here. So we will now resume from where we left off. Yeah, the point, I think most of you got the answer correct. So the point I was making is, if you look at this code, I'm just looking at the code right now. If you see it, the training of the network for each epoch in the number of range, for each row, that means for each input sample, I am forward propagating the input sample. That is, I am getting the forward propagation. Then I am asking, initially I am saying the expected values for all the outputs is 0. Then I am looking at, because the input already also carries the output as the last value. So I'm taking that last value and making that equal to 1. So the expected value will, so if there are two expected outputs, which become 0 or 1 in this case. So if the output of a particular thing is 1, sorry, if the output of a particular thing, so it can be, let's say this responds to 1 and this responds to 2 or something like that. So if the what we are doing is we are taking the last value and substituting that the expected value, that is equal to 1. So for this we are saying, for the first sample this should be 1, and for the second sample, depending on what is the expected output, we will make that expected output 1 or 0. So outputs can be 1, 2, whatever. So that particular position or that particular neuron, we are making it equal to 1 or 0, depending on what cell. So it will be this cell or this cell, which will become 1 in the output. So, and then we are computing the error in the output, depending on how, by computing the sum expected I minus output i's the whole square. This is the mean square error for all the expected values. That means for all these values, there are two outputs expected, and this is the output which is there. Then we do the backward propagation for each of the row and update the weights for each row. So update weights, the row has to be passed again because of the input. So we do that. So here if there are 5 epochs and each epoch has 10 rows, like in the present example, the weight update happens 50 times. Okay. Now, I will give you a little maths and then we'll come back to this code, to not this code, we go to another code, and then I'll talk about the changes which you will see and how to change that code. Okay. So now it doesn't ever happen like this. Okay, but there is a reason for that, and you should first understand the reason. So let me explain the reason first, and then we will talk about why it is done that way. Okay, so let me start with a clean page. So in real life, what happens is, okay, now before I do that, I'll use the traditional way of explaining this, which most of my colleagues in the industry use. See, the idea is, if you have a two-dimensional axis, you have loss on the y-axis and you have weights on the x-axis, the way each particular weight on a x-axis, then the graph has to be convex. Okay, and you have to detect this point, what should be the weight where the loss is the least. So you have to find the minimum. Now, right now, I'm not going to talk about the local minima or the global minima. I'm just going to talk about the minimum. So we have to work in such a way that if this is the loss function and it is plotted against weight, we have to work with the weights in such a manner that if the weights are here, we have to scale them up, that the slope will take care, and the low weights are here, we have to bring them down so that we reach this point. Now, let's say currently your loss is here. Okay, let's say let's get that point, that currently my loss is here. So this is my current loss, and I want to make my loss this much. So now I can go into weights by doing, if I do an update after every row, you know, the danger is I may not find convergence very fast. So, okay, let me just draw it. What may happen is, after the first update, I may swing my loss here, then I may swing my loss here. This is all loss. Okay, my loss is coming down, but it is swinging widely because each sample, each input that I am taking is causing an update to the weights. So the weights are getting updated very frequently. There is no time for the weights to give stability. So it is in a very zigzag kind of order that I may find, and sometimes I may skip this thing and I may go somewhere else. So there is every danger of that happening. The thing is, there are two problems in the current approach. There are too many weight updates, too frequent weight updates rather. Too frequent is a probably good word. Too frequent weight updates, that I'm not that worried. What I'm worried is, if you keep updating on every sample, every row, sometimes the weight will go like this. Sometimes the weight will get here, loss will come here. I'm obviously trying to minimize the loss, so I'm showing loss going up. But it's possible that the weight is such that the loss actually, because the loss is computed overall, and the loss per sample because of this weight update may actually shoot up. I'm at least here being generous and showing it go down. So this is not a very good thing to do, because when you have an input data, okay, you have an input data of, let's say, a certain number of samples. With each sample, if you start shifting weights, it is like reacting to every sample too much, giving too much importance to every sample. So if you have an outlier means a random sample which comes in, that will end up influencing the weights very heavily. Weights will very heavily influenced by outliers, because an outlier comes in, the weight will swing so wildly because that one outlier will make that weight update so much. Outlier means some random sample, some crude sample, something which is not fitting with the rest of the incoming data. If that comes up, then I'm going to swing my loss may go into some other thing with the next update, and it will be very, very wild, which is what we seek to avoid always. Every AI designer doesn't want that kind of a, what you call fluctuation in the weight updates to be so much. So what's the answer? The answer is, well, I have to update the weights. I have to change the weights because I have to move my loss down. Finally, I have to reach the weight which I've shown in the figure. So what is the answer, do you think, which I should do in order to stabilize the weight updates? There are two problems. As I said, I'm repeating them again. First problem is I'm updating the weights too frequently. I don't like that because there are too many computations will anyway have to be done, but I don't want the weights to change so rapidly. So it's like, I see, suppose I want to judge a basket of fruits, imagine I want to judge a basket of fruits. I just pick one apple from that basket, and depending on just one quality of apple, I start making impressions. Would that be right? Would that be a right approach? Or can you suggest a better approach? What do you think is a better approach? Currently, that is what is happening. I look at every apple, I immediately change my weights. I look at the next apple, I immediately change my weights. So first apple is very bitter. I get very upset and form one impression. That is what weights are. I form another thing, and I form another impression. And this becomes like, I look at one guy, make a decision. I look at another guy, make another decision. Rather than about a class, I pick the first student, answers well, oh, I am damn thrilled. If he doesn't answer them, we don't look at it. I immediately make a bad impression. What is the way I should actually look at? Am I doing it the right way? Or as a logical guy or a logical person, what would be your call? I mean, to my discussion, to my problem. What would you do? Okay. Yeah, I would like to hear a few opinions from your side, just to be able to appreciate, what is it that goes on in your minds when you are faced with this kind, because thinking is very important in AI. You have to learn to think the way AI thinks. So right now, the updates are happening too very frequently, and they are too very, what do you call, every time I'm seeing a row of data, I'm changing weights. Okay, so I'm not liking that approach. I think that's intuitively a wrong approach. How would you suggest I correct that? I'm looking at one answer. Okay, any better way of putting that? Ahmad, I'm looking at your answers. Sai Shivani, I'm looking at your answer too. They're good answers. Any deeper suggestion? Okay. So when you are saying sample, I'm still trying to see a word. I'm looking for a word. I'm not getting the word. All your answers look okay, look good, but I'm looking for a word. No, not really. The magic word is yet to come. I'll wait for a few minutes to get that word. Doesn't matter. See, you can't change anything with the inputs, Wallah. Learning rate should be stabilized. No, we'll come to that later. Something more fundamental. Think a little with us. Take an average of every few updates to give a big picture. I'm still searching, looking for that one word which will define what we are going to do next. Standardization is not the word. Normalization is also not the word. Okay, the word starts with B. B for Bombay. It's a very simple word. It starts with B. Bias? No, nothing to do with bias. No, no, don't throw arrows in the air. Ah, Rishik Garlipalli got it. Batch. Yes, the word I was looking for is batching. Okay, maybe I was asking for it in a wrong way, but good. Some of you got it. Very good. So I'm going to do batching and then wait for a batch of data before we apply the the updates. So I'm not going to apply updates for every sample. I'm going to accumulate a bunch of updates over a batch, and then I'm going to use the batch accumulation to update weights. Okay, so I'm going to play it that way. Okay, now I'm going to show you the code as I go through, which is changed from what it was earlier. And I will tell you where the changes are. I'll show you the old code and I'll show you the new code. And then you will understand why I'm doing batching. So before that, the argument for batching is something like this. Yeah. So the reason I'm doing batching is because, so I'm going to do batching. So what I'm going to do is, if I have a huge data set, after every, let's say 20 rows, for these 20 rows, as they are going, I'm going to do the forward propagation. I'm also going to do the backward propagation, because I'm going to do the forward propagation so that I get the outputs of every layer. I'm going to do the backward propagation so that I get my deltas populated. I'm going to get the deltas populated for every neuron as part of the backward propagation, because that does it well. See, if you imagine, for every neuron there is a weights key in the dictionary, which is the list of weights. I'm going to keep that. After the forward propagation, I get the output for every neuron. After backward propagation, I get the delta for every neuron. This is not a list. Sorry, this is scalar. This is also a scalar. Okay. Weights are a vector for every neuron, which connect the input to this. Output is just 1 for every neuron. Delta is also 1 for every neuron. It's a scalar. So this backward propagation gives me delta. Forward propagation gives me output. Okay. So this is what I have got. Now, what I'm going to do is, I'm going to keep doing forward, backward, and all that. But I'm not going to update the weights every time. I'm going to instead accumulate the deltas or the gradients. And once I accumulate all the deltas for the batch, and the batch is done, then at one shot, I'm going to do some averaging and apply the update. Okay. So that's what I'm going to do. And by doing that, I'll get more stability. And therefore, this is what is used in practice. We never do training one row at a time. We always do it like this, mini batch. This is called mini batch or batching. It doesn't matter. So all the samples in the batch is typically 20 rows or 50 rows. It can vary from program to program. So let's say 20 rows is my batch. In real life, they are far bigger. So I take a batch of, let's say, 20 rows. And what I do with these 20 rows is, I do the forward propagation of all the 20 rows. I do the backward propagation of all the 20 rows. So all the delta is accumulated. Then I don't do any weight updates while all the 20 rows are being processed. Now, I don't do update of weight after every sample like I was doing earlier. And what I do now is, I say, I will update the weights only after the batch is finished. And I'll take a mean or something of all the deltas which are there for every sample which have been accumulated. And I will accumulate all the deltas. And therefore, I will do the batching. After batch, I'll apply the update weights. So now, if you had 1,000 rows, or let's say if you had, okay, let's take the original example. If you had 50, sorry, I think let's make it more realistic. Let's say you had 1,000 rows in one epoch. So in one epoch, there will be 50 updates in this case, okay? Because after every 20 rows, we'll have an update. So the weights updates will be more stabilized. They will be not very random. They will not, what do you say, fluctuate or oscillate after every sample. So all the outliers will not affect the update dramatically. They will kind of be kind of buffered by the rest of the data, which is not outlier based data. So that is basically the theory behind how batching or mini batching happens. And mini batching happens all the time. Never is the way I just described the code. Actually, what I described the code, which I gave you, which we saw on the site and all that, is called SGD. Okay, to just give you names, it's called SGD. Okay, stochastic gradient descent. Stochastic gradient descent. That's the code I gave you, original code which we are looking, where updates were happening for every row. That is called stochastic gradient descent. That is very stupid. What is common, actually this changes often, and I'm going to explain to you all of that in detail, is called mini batch SGD. So what we are going to show you now, the code is batch or mini batch with SGD. Okay. So instead of doing plain vanilla SGD, which is sampling, which is updating the weights every time, I'm going to do batch based SGD or batch with SGD, which is I don't do rest of my forward propagation, backward propagation remains the same. My delta computation remains the same. What changes is the frequency of updates. I do it after every batch. So I have to hold all the gradients and the deltas, and I will hold all of them, and I will apply them all at one shot. So I need a variable to accumulate all the deltas. So I'll create a variable, or I'll create a data structure for accumulating all the deltas, and I will take them all after the end of the batch and use them to alter the weight. So let's see the changes to the algorithm which have been done by looking. I'm now going to show you the code of mini batch with stochastic gradient. It's called no, this is stochastic gradient descent. Now this is called mini batch gradient descent neural network from scratch. Mini batch it's called, but it can be also called mini batch with SGD, not pure SGD. What you saw was pure SGD. So now we had asked, a very simple thing we did, just to share this with you, how you should use ChatGPT. We explained what we are going to do to ChatGPT and said, look, I want you to modify this existing code and give me a code which does exactly what the earlier program was doing, but applies the updates not every time after every sample, but accumulates the gradients across the batch. That is, accumulates the deltas across the batch, and then applies after the batch is over, it applies. Okay. So now we are going to walk through the new code. We are going to say what remains same and what alters. This we have not done. We have borrowed it shamelessly, as all smart people do, from ChatGPT, and use that code from ChatGPT. And if you think you should write this code, you are an idiot, because that's not what you should learn. You should learn what the code is, not how to use ChatGPT to create the code. What code is to be created is more meaningful than, and what changes are done by ChatGPT to make that happen. This is the new way of learning. So take the original code, give it to ChatGPT, ask it to do what we asked it to do, that is convert it from SGD to mini batch SGD, and you'll get something very similar to what we are seeing on the screen. Okay, now we are going to just quickly walk through where the changes are. So here there are no changes in the initialization of the network. In the activation of the network, that is computation of the Z, there are no changes. Then in the calculation of sigma, there are no sigmoid, there are no changes. In the forward propagation also, there are no changes. In the transfer derivative, no changes. Wait, aram se, aram se. In the backward propagation also, there are no changes. It's the same story. Where we are computing the errors in the backward propagation, and then we are in the backward propagation. If you see, is the same story, just to convince you that we are computing the delta for each neuron in the backward propagation. I am hoping that everybody is convinced that that we are not doing anything strange. We are basically ensuring that forward propagation code has remained the same, backward propagation code has remained the same, and now we are going to the changes. Now, at this stage, I pause and I will tell you a few things. This is not to say something against somebody, but I have seen a lot of videos on the internet which seem to teach, stochastic gradient, mini batch stochastic gradient from very popular people. Honestly, they try to do a good job, try to simplify stuff, but honestly, they don't teach any real stuff. They are all, I mean, I will not say all is a very strong term, but 80% and 90% of them, I have seen their viewership. The viewership is very big, but the quality, believe me, is wrong. I mean, quality is poor is an understatement. I don't like people who sacrifice simplicity for the sake of incorrectness. If you can always sacrifice complexity, make it simple, but you ought to be correct. And lot of these popular people who talk about internet, about all these, AI teaching on the internet, I have happened to see a bit of videos, popular videos which some of our people have recommended. They are horrible. They never touch about the code changes. Their code changes is writing a bit of pseudocode and saying this is how it works. That's bullshit. There are glaring mistakes as to the way they talk about it. Many of them don't even understand how the updates are to be applied to every weight. Every weight has to have a different update. This point is missed in almost everywhere. And they end up creating in people's mind something which is easily digested, but something which is wrongly digested. And then I have problem with these people when I bring them into my AI school, where they come with they're looking for something very trivial. And when it comes to that, they find a little more complexity, they immediately, no, this is the easier video, is easy. No, I'm all for ease of understanding, but not at the cost of truth or cost of correctness. So you guys have to guard yourself against these kind of lectures which are going around on the internet. There are many of them, some of them from Indian authors, Indian teachers also, but they are not good. They seem to be easy to digest, very simple, but unfortunately, when I looked at them, that was the motivation for starting this series, that I thought this is the right way to teach in association with code. Teaching without code is like telling you, like some people give me the analogy, it's like saying, standing in the bank of a river and saying, now can you swim? Do your hands like this, do your feet like this, move your body like this, and you can swim. That's a bunch of bullshit, bunch of garbage. That's not how, without code, if you explain something, that is how I feel. Explaining something any idiot can do. Connecting the explanation to the code in today's world is super important, because finally we want engineers to implement those ideas, not talk about them or talk about it conceptually. Oh, I don't get it in the code, you see, but conceptually, this is what it means, bullshit. And you learn to call that as bullshit. Okay, I'm hoping that you get the point. Okay. Okay, now we have established our basic premise that we want to update at the end of every batch. Okay, now, so what we have to do? So when we have to update at the end of every batch, we need to accumulate the gradients. So I have to create a data structure, which I have to initialize first, which I call the gradients data structure. Now look at it, it's very easy data structure, which is getting created. This is to keep the accumulation of all the deltas and the gradients. So I start with gradients, go through all the layer because each layer needs gradients, and each neuron will need a gradient, just like delta. So layer grades dot append 0, 0 for each neuron. Now here is where the point comes. Do you need, okay, what is this data structure going to look like? So the first is the number of layers. So if there are layers, so you have a list of layers. Then for each layer, you have a bunch of neurons. So there is a list of neurons associated with every layer, right? So first, there is a list of layers in any network. With every layer, there is a list of neurons. With every neuron, for each neuron in a layer, we have a dictionary, right? So now what we are doing, you see there, layer grads is a list. Layer grads is a list, this list. So for every neuron in the layer, okay, for every neuron, suppose there are, okay, so this is what, this is each neuron. So this is, each one of them represents a neuron. So for every neuron, I have a list which is maintained. This is per neuron, which is the list of the accumulated gradients. How many gradients will I have? As many as the number of weights. So if I have, for each weight, I have to maintain, because see, dl by dw1 is different from dou L by dou W2, different from dou L by dou W3. For each weight, see this, that's why this list is created like this. Initialized to 0. So now this is all zeros. How many zeros? Depends on number of weights associated with that neuron. That is basically the size of its input layer, right? In other ways. So again, let me repeat. So gradients is a three-dimensional story. First dimension, this is the layers. For each layer, I need to maintain the gradients. For each neuron, I need to maintain the gradients. How many gradients should I maintain for each neuron? Depends on the number of weights which are associated with that neuron. So if there are 3 weights associated with, that means there are 3 inputs associated with the neuron. You need to maintain 3 weights with that neuron. Sorry, 3 gradients with that neuron. So as many number of weights, that many number of neurons, that many number of gradients. So this is the grades. Grades associated with each weight. Okay. So once again, layers. This is the layers, the number of layers. It's a list of, then for the whole network, I need a list of layers. For each layer, I need a list of neurons. For each neuron, there are many weights associated connecting all the inputs to that neuron. So for each of those neurons, for each of the inputs, I need to keep weights. And for each of the weight, associated weight, I have to keep the gradient, because these updates have to be done to every weight. Now this point often is missed by most of the popular lectures because they never get down to this data structure. So we have to do this thing at the beginning of every batch. This has to be, this 0 gradients has to be called at the beginning of every batch, because the accumulation of these gradients, and you'll see how it gets accumulated. These accumulations of the gradients is done at every batch, applied at every batch, and then zeroed out, so that the next batch, the gradients will again accumulate. Okay, so that's how this story is built. Okay, now let's look at the code once again. So this change, this is a new algorithm, this is a new function which has to be brought into the code. This has been brought by the mini batch gradient descent. So this is the first change which we are seeing. Then this is the second change which we are doing, which is accumulating gradients. Now, accumulating gradients has to be called after every sample. We will after every back propagate, we will take it and apply it and accumulate all the gradients, all the deltas. So what is a gradient? Basically, it is the delta into that input. So that is the one which is to be applied to make once multiplied the gradient with the change, it will give you the new weight. So now look at this code for a few minutes. It is accumulate gradients. This is just accumulating gradients. It's not applying the gradients. When is this done? This is done for every sample, but the updating of the weights is not going to happen. Only the gradients are going to be updated. So just look at this code and try and understand what's happening here. So accumulating the gradient this is how it happens. So network row, because you need the input, and grads. Grads is the data structure which I just showed you, that list of lists. Okay, so now how do we start? For the first layer, the network is obvious. It's the input row, except the last bit, which is the output. If I equal to 0, this applies. Else neuron output for neuron in network I-1. So if I am at a particular layer, the previous layer's output is for all the other layers except the first layer. For the first layer, the actual input is this input minus obviously the last column. So that is how this is taken. This we have already seen in an earlier code. This is how the input is taken for the first layer and subsequent layers. So we know what is the input for any layer. And we are going through all the layers from the beginning to the end. Layer is equal to network I. Layer grads is equal to grads I. Okay, that is for every layer we are getting the network. So that will give us access to all the neurons, and this will give us access to all the gradients associated with that layer. Now and this is just an enumeration of the layer. This gives you the enumerator. So for each neuron in that layer, and for each input associated with that neuron, remember one weight is associated with every input of every neuron. So we are now going through all the neurons of a particular layer, and we are going through all the inputs, because with every input weight is associated. For all the inputs of that neuron, we are looking at all the inputs of that neuron. Layer grads NDX J. Now what does NDX stand for? NDX is for which neuron is this. J is which input of that neuron. So basically this represents for this input is connected to that neuron. So that weight, okay, this represents a particular weight in a way. And for that weight, what should be the update which should happen? The update that should happen is the delta which is sitting on that neuron, okay, the neuron delta into inputs J. So this is the gradient which will be used. Inputs J is the input to that layer. So we're going to go through all the inputs, and this is going to accumulate all the changes across the inputs which are going to be applied. So if you give the picture, here is the picture I am trying to say. This is one neuron in one layer. Let's say there are 3 neurons here which are all connected to this. Just imagine this. We are looking at one neuron. We know the delta of that neuron, and we also know the input of everyone. So we know x1, x2, x3, and now we have to apply the weight gradient. We have to accumulate the gradient. So layer gradients NDX, the first thing for that particular layer, the first neuron. This indicates which neuron, and this indicates which weight in that neuron I am looking at. So I am looking at this first, this second, and this neuron, which is the weight in that neuron I am looking at. For that neuron weight, multiply this with this input, multiply it with this input, that will affect the gradient here. So basically it is dou L by dou W1. Imagine this is W1 is equal to the delta which has there on that neuron, delta times the input, that is x1, because everything else has been already accumulated. So that will be the weight gradient for this weight change. And how we'll apply the gradient, we'll see. But at this stage, we are only accumulating the gradient for this. Okay. So NIDXJ is for this weight. Now, this weight will also be connected. So we do this for all this for this neuron. Then we go to the next neuron and similarly we accumulate it. So this gradient, so this x1 is also connected to another neuron here, like this, through some other weights. Now this delta is the weight change for that also, which has to be, which will affect this weight. Okay. So all that is getting accumulated. You see there, that is delta into input j, and that is getting summed over for every one. So it is getting summed over all j's. What are j's? The length of inputs. Because see, this weight is getting, this x1 is affecting this and a lot of the other guys. Okay. This delta. See, this input j is affecting this. So this gradient is getting affected and then a lot of others are getting affected. Okay. So this is how we are taking it back, and we are computing the change dou L by dou W. We are computing. We are not computing the weight update. We are just computing the gradient. So the gradients have been computed for each and every neuron. Okay, just think. You can look at this code later. Just think that all the gradients have been computed. Now have been accumulated. Okay. This happens after every row, but this apply gradients. Now let me just show you the training and then you will come to apply gradients. Now we are almost at the end. Okay. So see this, look at the change we have done. Can we push it a little ahead? Forget that shuffle and all, that is not needed. Now you are going through the entire range. Now there is a small change here. Look at the way we are training. We are going from 0 to length of data, batch size. We are going to go only for batch now. And the batch, the data which we are going to give to the network is start to batch size, current batch, length of batch. And at the beginning of every batch, this is going to iterate through every batch. So at the beginning of every batch, we are zeroing the gradients. Now we are going and processing the batch. Can you come down? Okay. Now look at the code carefully. For every batch, what we are doing, for each row in the batch, we are looking at the inputs. We are doing the forward propagation. We are finding out what are the expected values. Then we are accumulating the errors. Now comes the important part. We are doing the expected outputs. We are doing the backward propagation. We are accumulating the gradients, but we are not applying the gradients. So after every backward propagation, the gradient will absorb the change which needs to be done, but it will not apply the change. The gradient will be accumulated. See this. The gradient means you think of it as delta, is being computed every time for every row. Gradient is computed for every row, but nothing is applying. So this is the row in batch. Now you see this output, this code. This is the apply gradients. That happens at the end of the batch. So I'm accumulating all the deltas for every row, just like I was doing earlier in a regular stochastic gradient. But at the end, I'm applying all the effect of all the gradients at one go. Therefore, stabilizing my application. I'm not fluctuating the weight change every time. Okay, I'm not oscillating. I am watching for an entire batch. What are the gradients? Computing the gradients, adding up all the gradients, and now I'll take the average of the gradients and kind of apply it to the network. Okay, and now I'll have an apply gradients which is done at the end of every batch. So now look at that, what it is doing. It is just very, very simple code. So you have for go through every layer in the network, for look at every neuron in that layer, forget about these indexes, these are numbers. For J in range of length of neuron, for every weight associated with that neuron, look at every weight associated with that neuron, get the, so I is the neuron, J is the weight associated with the neuron. For every grad ij, compute the neuron which has been accumulated and divided by the batch size. This is taking the mean gradient, mean of gradients. This is because, look at it, it's taking it in the denominator. It's by. It's taking it in the denominator. So it's computing the gradient on an average. And then it is updating the weight of that particular neuron, that particular weight of that particular neuron by learning rate times gradient ij. So this is what it is doing. This code is the key code. So this is what is happening. I am taking the whole batch, computing the gradients. You can think computing the deltas for the entire batch one shot instead. And I hope some of you are able to appreciate the difference between this code and the earlier code, where after every weight, after every backward propagation, I was applying the weight change. Here what I am doing, after every back propagate, I am not applying gradients, I am accumulating the gradients. In a gradient list, I am accumulating all the gradients. Once I have accumulated all the gradients, okay, what I am doing, I am taking the average of the gradients at the end of the batch, depending on the batch size, dividing it by batch size. I am taking the average change, and then I am making the weights change based on that average. So this is how my weight update is being done. Okay, this is how the weight update is being done at the end of every batch. This is the change. So you need to appreciate this code because this is the code they have taken. This kind of code they have taken and made it into tensor. And that is how PyTorch, tensor algebra, all of that has emerged. All of this becomes automatic. It goes under the carpet. And what we are trying to do is learn it from the core and then figure out how to push it under the carpet. Okay, I don't want you guys to emerge as engineers who don't know what happens under the carpet. So all of this will be invisible when we go to higher level coding. But I don't want it to be invisible. I want you to fully perceive what do you mean by batch gradient? What do you mean by stochastic gradient with mini batch? Okay, now I know the number has already dropped to 125. That also indicates it's a good thing that it drops because we expect only a certain number of people to understand. And we expect most of you not to understand because that's what happens. But I'm hoping at least some of you will pull up this lecture and then listen to it and get the hang of it. So in the next session, rest of the code by and large remains the same. You can look at it if you want. We'll post it also, or you can generate it also. This is the significant change. That is, you need to introduce a gradient data structure. You need to show after every sample how do you accumulate the gradients. Then after every batch, how do you do the averaging of the gradients and apply it to the weight change. Okay, so this is where I am and this is where we are. In the next batch, in the next class, I will show you how today's optimizer, which is basically momentum optimizer and the Adam optimizers, how do they work and how do they are the real optimizers used. And once we know that, then we know how these things work from within and then I will play a little bit with the loss functions, and then we will start our PyTorch in full understanding what is happening under the hood.